Bismillahirrahmanirrahim. Assalamu alaikum. In this short video, we talk about one variant of K nearest neighbor that focuses on improving the computational complexity of kNN. In the previous module, we talked about storage complexity and time complexity of kNN. Uh, we talked about we derived computational complexity of kNN, and that turned out to be of the order n times d, where n here corresponds to the number of points in your training set, and d corresponds to the dimension of the feature space. Due to this dependence on n and d, kNN is referred to as a lazy algorithm because the computation complexity grows both with the increase in the dimension of the feature space and also with the size of the training data. And every time we need to carry out these many computations to make predictions. The question here is, how can we make it faster? Uh, as it indicates here, we can either reduce d or we can either reduce n to reduce the overall computational complexity. In order to reduce d, that corresponds to reducing the number of features we can use to carry out predictions. Reduction in d is referred to as dimensionality reduction. That is effectively reducing the number of dimensions uh, in the feature space to carry out predictions. The overall idea is that, for example, if you have a data or you have images, for example, you have MNIST data. So in MNIST data, we have 784 dimensions. The feature space is 784 dimensional. Uh, we may not need all of the dimensions, all of the pixels to carry out predictions. We can do some manipulation on the data to reduce the number of features and to bring it down significantly so that we use less number of features uh, to carry out predictions, and consequently the kNN or any other classifier would have to deal with less number of dimensions. And the most commonly used methods to carry out this dimensionality reduction includes feature selection that is based on by choosing some metric, for example, correlation coefficient, to reduce the number of features. In the very first video, I briefly talked about this feature selection dimensionality reduction. If you have two features that are correlated to each other, you only need to keep one feature. You do not need to keep two features because one feature is effectively explaining the variations that are defined by the second feature. So yeah, we'll talk about this in great detail later in the course. Another method that is commonly used for reduction in dimensionality is principal component analysis, abbreviated as PCA. We will also cover this in the second half of the course. Uh, I can give you a very quick glimpse of PCA. So PCA corresponds to manipulating data by representing it along the dimensions in the higher dimensional space such that those dimensions capture maximum variation in the data. So in a higher dimensional space, we define new bases, we define new dimensions, and those dimensions are chosen for a given data such that along those dimensions we have maximum variation in the data. And then once we find those dimensions, we project the data onto those new bases. Uh, the dimensions along which we do not have significant variations, we can drop those dimensions, we can drop those bases, and effectively we can reduce the overall uh, number of features we can use for predictions. Okay, we will talk about this PCA in great detail, that how do we formulate a matrix from the data, how can we carry out decomposition of the matrix to find these principal components, and how can we project our data onto those principal components. Okay, but in today's module, we focus on devising an efficient method to find nearest neighbors. Right. So if you recall, this computational complexity of kNN and D is due to two reasons. Okay, the primary reason is we want to compute distance of your test point to every point in the feature space, right? And that is the origin of this ND. Uh, and we need to compute these distances to find nearest neighbors. But the question here is, can we find can we devise some more methods, some alternative methods that can overcome this computationally expensive operation of computing distances? And we will talk about one variant of these methods, and that is KD tree. In fact, many variants have been proposed in the literature to overcome or to make kNN more computationally efficient. But in this very short video, I will give you a quick overview of one of the variant, that is KD tree. So what is a KD tree? The name suggests KD tree corresponds to k-dimensional tree. It is nothing but an extended version of a binary search tree in a higher dimension. In a binary search tree, we construct a tree by splitting data into two halves at the root node and progressing in a similar fashion, and keep on constructing a tree by splitting data at each tree level into two halves. Uh, but when we extend this to higher dimension, we need to define the dimension along which we should be splitting our data. We will use the same concept. We will split data into two halves at every tree level, but we will define the dimension. We will have to pick a dimension along which we should carry out splitting. And uh, we split this dimension usually randomly, but there are some variants in which they propose to use large variance dimension for splitting of the data. So this large variance dimension enables us to construct a tree that is balanced. That means you have almost equal number of uh, data points in each branch of the tree or along each branch of the tree. Right? Once you define your splitting dimension, you divide the data into two halves by splitting around the middle value, and we keep on progressing this. But at each tree level, we pick a different splitting dimension. This is the only difference from a binary search tree. And in binary search tree, we only have one dimension, and we stick to that dimension, and we keep on splitting data. But in KT tree, at every tree level, we pick a new dimension to split the data. Okay, to illustrate this, let me give you one example, and we will construct KD tree for a given data. Right? So for convenience, we take D is equal to 2. This means we have a data in a two-dimensional space, and we assume that we have these data points. And for these data points, I want to construct this tree-like structure, this binary tree-like structure. In fact, this is a binary tree, but the difference is that here, we have this splitting dimension, right? And if you see, I will be carrying out splitting at the root level with respect to x1, at the child level using x2, and if I had x3 here, I could use x3, but I don't have x3. I'm in R2, so I will be using x1 again, and so on and so forth, right? I am free to choose any splitting dimension at every level. So I could choose x1 at level 2 as well, right? Okay. Okay, let's populate this tree. So we have this data, and at the root level, I want to carry out splitting with respect to x1. Right? So if you see x1, we have 2, 3, 5, 8, 10, and 13. So we have 6 data points, and the middle one would be, we should choose the first median. that would be 5, 4. So this would be my first data point, the middle one that corresponds to dimension along dimension x1. So I will be using 5, 4 in the root tree. And once I have this parent node 5, 4 here, this splits data into two halves, right? So one half on the left hand side and one half on right hand side. And please note, this splitting is with respect to x1, right? So this is splitting I get. So I get 2, 6, 3, 1 because 2 and 3 are less than 5, and I get 8, 10, and 13 because they are greater than 5. Right? Okay, now I need to choose what should be coming in this this green, this one here. Right? Okay, I should be splitting with respect to x2. Right? And if I sort these two data points in ascending order with respect to x2, I get 3, 1, and 2, 6. So again, I choose the first one, 3, 1, that comes here. And what about 2, 6? Right? What do you think? 2, 6 should be going to the left, 2 should be going to the right. अब इसको सोच लें आप, अभी इसको पॉपुलेट करते हैं, right? Okay. Let's talk about the right hand side. Right? On right hand side, we have 10, 2, 13, 3, and 8, 7. So 13, 3 is the median value. It splits data into two halves. Right? 8, 7 should be on the right, and 10, 2 should be on the left. Why? Because 7 is greater than 3 and 2 is less than 3. Right? Or I should be very precise. I can say if it is greater than or equal to, I will pick the right hand side, and if it's less than or equal to, I pick the left hand side. Now, what about this 2, 6? 2, 6 should be towards the right because 6 is greater than 1. Right? So we should have 2, 6 here. And similarly, 10, 2 should be here, and 8, 7 should be here. And we are done with all the data points. If we had more data points, we could keep on populating the tree. I hope this is clear that how can we construct a KD tree. So this KD tree, in fact, is carrying out splitting of my feature space into small cubes, into small sections. And to visualize this, let me illustrate. Okay, so we have this KD tree, and if I visualize this division, this splitting of the data in R2, so I have generated these data points. What I had, right? So the first splitting 5, 4, right? So that is, if you recall, that is along x1, right? So this is my x1 and this is my x2. Right? So the first splitting is along x1, so it splits data into two halves. 2, 6, and 3, 1 left, and 8, 7, 10, 2, 13, and 3 to the right. And the next splitting is along x2, right? So you get splitting along 3, 1, and you get splitting along 13, 3, right? And if we go further down to the next level, we get again splitting along x1 and splitting along again x1, right? So so what's the basic idea? The root node splits into left and right by x, right? And when we have these odd depth partitions, we are splitting into up and down. So we're getting left and right at even depth partitions, and we're getting up and down partitions for odd depth partitions up and down. If you see, so we are getting regions of R2, and in fact, if you go to higher dimensions, these rectangles would be cubes, or the precise name would be hypercubes. So the KD tree is partitioning my feature space into hypercubes, right? So uh, this is the visualization of splitting of the feature space by KT tree. Okay, let's talk about connection of KT tree with kNN. That how can we use this splitting or how can we use this partitioning of feature space to find nearest neighbors efficiently. Okay, to illustrate this, I can take this point, 9, 4 as my test point, right? And I want to find the nearest neighbor. I will start from the root node, right? So I will pick 9, 4 and I will compare with this 5, 4, right? The splitting at this level is with respect to x1. So 9 is, I will compare 9 with 5. 9 is greater than or equal to 5. Therefore, I will follow this dimension, this branch of a tree, right? And then at the next level, I will compare x2, which is 4, with 3. So since 4 is greater than 3, I will follow this. And I will keep on traversing this tree until I reach the bottom node, the last node of the tree, right? And when I reach the last node, right? So I'm in 8, 7, right? And therefore I should be looking for the nearest neighbor in this region, right? So in fact, this should be, this should be only this one. Okay, I will comment on this why I've chosen this all this, right? So I will be looking only this one, so this region, right? And I will keep on scanning this region, right? So I will traverse back, right? So I will say 8, 7 is, hang on, 8, 7 is my nearest neighbor, and this is the distance to my nearest neighbor. Right? So there is an issue in this one, right? And the issue in this one is that you may miss neighbors. So for example, if this red point is somewhere, let me try. Pen and ink color should be red. Okay, if this point has somewhere here, right? Then this 10 to is nearest, is relatively, is nearest than, nearest to this point than 8, 7, right? But since we're looking in only in this region, our algorithm would still return 8, 7. And the next nearest neighbor would be 13, 3, right? So I will get this 8, 7 and I'll get this 13, 3. But how to overcome this? The trick, the magic is that, okay, you start from 8, 7 and you keep traversing up. So you reach 13, 3. And once you reach 13, 3, instead of further going up, you should also traverse in again in the child node. So when I reach 10, 2, that means now I should be scanning. In fact, from 8, 7 to 9, 10, 2, I should be scanning because I'm reaching from the right, so I should be scanning this point as well. So 10 to, in this way, I won't be missing neighbors. Right? So using this trick, obviously this comes at the cost of increase in the computational complexity, but I can overcome this problem with KD tree, that I should not miss neighbors. Right? So if you use classical KD tree, you may miss neighbors, but if you use this trick, this variant, you can overcome this problem. Okay. So that was a very, very quick overview of KD tree. So I can summarize the KD tree. So KD tree enables significant reduction in the time complexity. And this complexity would be simply order log n if you as compared to n. In fact, it was nd, but if you just only talk about the nearest neighbor, because you will be comparing distances. So order log n, it has, it significantly reduces the computation complexity to find nearest neighbor. And obviously it comes at the cost, and the cost in achieving this reduction is that you get a computation overhead, because now we need to construct a tree, right? And the computational overhead to construct a tree in worst case would be order n log n. We also need to allocate space to this data structure, and the space complexity is order n, although this won't add much to the complexity of the overall kNN, because for overall kNN, we already need n times d storage. Right? There's a possibility that KD tree may miss neighbors when you search for the nearest neighbor, but now we know how to overcome this. And finally, we note that this is also with kNN, that performance of classifier or performance of predictor can degrade with the increase in the dimension of feature space. And this is our this is our next topic, the curse of dimensionality, that what happens when you, what happens to the performance, what happens to the distances, what happens to the neighbors when you increase the dimension of the feature space. Okay, so we stop here, and in the next module we will start with this concept, curse of dimensionality. ठीक है जी, अपना ख्याल रखें, सी यू इंशाल्लाह, अल्लाह हाफिज़ जी।